Alrighty, somebody tell me a component they picked and what it does. Okay. So what do the control rods do? Can you change that word? No. Anybody want to pick a different word? I like absorb better because when you say block, I kind of feel like, I don't know, like a block shot basketball. Like it just gets deflected and it's going someplace else. So it makes it out to sound like maybe it hits the rods and then deflects and then it could hit something else. When it's absorbed, it's like it's consumed. Can just stop the reaction altogether. Okay, what else we got?
You got the lead shielding on the inside of the concrete shielding.
So tell me why we have a lead shield.
To keep the radiation and anything not to
More specific than that.
gamma rays in.
Okay. What else we got?
When I read this question, I was like, oh, it's the primary, the secondary.
Well, I do ask that question sometimes. Describe the loops. So everything that's radioactive is inside those fuel rods. If it's outside those fuel rods, something horrible has happened. And the source of heat. Okay. So how does an atom end up becoming stable? What needs to happen? I feel like several of you, actually, I don't think anybody answered that question correctly, at least what I was looking for. On the lab, there was a question about lead-206 being stable, non-nuclear. I got half answers, but I didn't get a full answer. So when we first started talking about nuclear here, what did I say was the reasoning behind the nucleus being radioactive?
Because it's decaying, or there's a decay happening.
Yeah, but why is that happening is the question.
Because it's releasing.
But why is it releasing?
It has something to do with not having the magic number of protons and neutrons.
Bad ratio of protons to neutrons. I have to leave it like that. I can't be more definitive about it because there isn't a number. It's not like 2.67 neutrons per proton is the number because it varies per isotope. So for hydrogen, 1 and 0 is fine. 1 and 1 is fine. 1 and 2 is not fine. So every element is different. For carbon, 12 or 6 and 6 is great. 6 and 7 is okay. 6 and 8, not okay. So it's a bad ratio for protons and neutrons. And there's one other aspect to this, though. We talked about with bismuth. after 83 protons, it doesn't matter what the ratio is. The thing is radioactive, period. Anything after number 83, polonium on up, all isotopes, regardless of their proton-neutron ratio, are radioactive. How come it, or why would it be difficult for a leak to reach the river? I guess I should have said in that thing up there.
Because the radioactive material in nuclear power plants is not actually near the water source. It's tucked away.
It's locked away in the fuel rods. And those fuel rods are these are in primary loop. Not in contact. So the primary loop water around those fuel rods, they're not actually in physical contact with anything that's radioactive. The radioactive stuff is inside the rods. So the water itself isn't actually radioactive. But that water that doesn't come in contact with the actual nuclear stuff has no contact with that water has no contact with the secondary loop, which has no contact with the condensing loop, which has no contact with cooling loop. So in order to have it leak, the fuel rods would have to leak, the primary would have to leak into the secondary would have to leak in the condenser, and the condensing loop would have to leak into the cooling loop, and oh, well, yeah, the cooling loop would leak into the river because it's right there and it's dumping into the river, but all the pumps would have to keep moving, right? You can't just have it leak in one spot. Like, I need all the water to be moving, and what happens when any one of these things breaks? They turn the whole thing off. They insert the control rods, turn everything off. Usually what happens is you have a leak somewhere in the secondary loop because it's at a very high temperature and a very high pressure. Not uncommon, a pain in the butt, but not uncommon. Then you just turn the reactor off, get the pressure down, get the temperature down, fix the secondary loop, turn everything back on. So people who claim that the Trojan nuclear power plant leaked into the Columbia River, I don't mind you looking for nuclear leaks, but go to Hanford because they're definitely leaking. The power plant's not leaking. Comes out of the top of the cooling tower. Just some H2O vapor. If you put cloud, I'd be good with that. Did you guys find SCRAM?
Safety control rod arm gap man.
Cooler than that. E? Is there an E on that? Is AX not actually a word? And I've just always thought that. Cool. All right. English. Okay, so that sounds pretty cool, right? I'm the safety control rod Axeman. It was a horrible job.
Is it?
A phenomenally dangerous job. Gotta be.
Are you like cowboys at like nuclear camp world?
No,
Okay.
more like the canary of canary in a coal mine. Not a great job to have. Let's see, is this under nuclear? No. How about this under stack? Really? All right, let me back up with that. There we go. This is a drawing of the first sustained nuclear reaction that was based on the equation that Lies Meitner came up with, that cocktail napkin thing. Happened in the no longer, definitely the defunct gymnasium, a defunct gymnasium at the University of Chicago. They used this one because it was actually underground. And so these are bricks, and the bricks alternate between lead bricks and just regular old bricks. And inside there is a nuclear reactor. Not one that will generate electricity, but a containment facility like all the stuff that you saw, minus the water in that first, where all the control rod and the containment core. So do you see this rope? Yeah. There's a guy right here. That guy is the safety control rod axeman. And if the shit started to hit the fan, what was he supposed to do? Use the axe to cut the rope, and then the control rod was going to fall in there and then turn the whole mess off. But we'll find out a little more about this later. But the issue with this is you're not going to be fast enough. I mean, if this went south, this thing explodes in like a millisecond. So you're not even going to know what's going on, and you're already going to get hit in the face with a bunch of bricks. So he was standing there on just like some scaffolding, and everybody else was like literally 30 feet away behind some glass, so they weren't protected any more than anybody else. But it worked. It was okay. He didn't have to actually axe it. They just slowly put it back in. So they slowly pulled it out. The readings that they got were lots of gamma radiation, lots of neutron production, and it was continuing, which meant that the reactor at least reached critical or supercritical state, which meant that more neutrons or the same amount of neutrons were being generated as were being used during each nuclear reaction. And at that point, they realized we could use this for lots of stuff. The term, though, is still used anywhere there's a nuclear power plant. Like if we needed to turn the reactor off on the ship for a drill or something, that's what we said, scram the reactor out. And somebody would flip a switch and the control rods get thrown back in. All right, so cool. This is all confused. Thinks there's a keyboard here now. There we go. Okay, fission and fusion. I know we didn't talk about fusion at all, but we were going to talk about that today. So what do we got?
Fusion is when there's two smaller nuclei get forced together and become one larger nuclei. Our sun uses fusion.
So the fusion is two small nuclei come together to make a larger nuclei and a whole bunch of energy. And the fission is a large atom like the uranium-235 gets split into smaller atoms and energy. Which one of those provides more energy? The fusion. Fusion provides considerably more energy. How come we're not using it?
It's difficult. It's hard to do.
Yeah, why is it hard to do?
Temperature needs to be like, it's like 15 million Kelvin or something.
That's what happens at the source of the fusion reaction. We don't have anything that can withstand that yet. I mean, we're trying really hard. The main idea is that we would take the two deuterium atoms and crush them together to make the hydrogen atom or the helium atom, and there wouldn't be anything in physical contact with it. What we've been doing is creating giant magnets that produce a magnetic field that hold everything in a spot. So imagine instead of just like physically touching stuff, you've got magnets everywhere, and the magnets are holding everything in the middle. So there's nothing in actual physical contact. The problem is the magnets' range isn't large enough. No matter how big we have built them, we haven't been able to build them big enough so that the reaction that's happening in here can be cooled enough to make sure that the magnets don't melt or the wires don't melt or the whole thing doesn't overheat. And it's been going on for 30 years now. We just keep tweaking it and trying to figure out a different way to do it. But it hasn't worked out for us. So you can imagine my frustration when I see this. So when you read this, what after writing that answer for the fusion and fission, what's wrong with this? What's wrong with the first part, the fission?
This is totally breaking apart the.
It would be awesome if that happened, right? Why would it be awesome if that happened?
Fast decay.
No? Oh, well, there'd be no decay, right? That's just neutrons, which can just be absorbed by whatever, concrete or water or something like that. And then hydrogens. So what? I just made a bunch of acid? Okay. There, put some base in there and it's taken care of. The water inside a nuclear power plant is basic, so it wouldn't care. But that doesn't happen. It makes that rubidium and cesium that have very, very long half-lives. So that first thing was like, is this a joke when I read that? And then I read the next one. What's the problem with this one? The major problem with this one?
This is a lot more.
A small amount of energy is released. The sun evidently has a small amount of energy. So I got very frustrated with this. And I tried to track down the author. It was an AP source. Do you guys know what the AP is?
Like advanced placements.
No. With reporting, with news. So if I have a newspaper and I've got a spot in my paper that's blank because I don't have enough stories for it, I could go to the AP wire and find a story and pay them a little bit of money and then put that story in my paper. So this was an AP article, and the person who wrote it wouldn't respond to me or didn't get my messages, and the AP wouldn't give me any more information on them. So I'm like, did they really come? I mean, they cited a source, right? Did they really call UCLA's physics department and they gave him these graphics? So I called UCLA. And they said, we don't have a physics department. Oh, cool. Do you have a science department? Of course we do. I'm like, okay, can I talk to the science chair? Yes. So it was an AP article, so I was actually able to find it online. So I talking to the science chair, I'm like, what's your email? Sending you something. Read this article. He looks at it for 4 seconds and he's like, what the hell is this? I'm like, I don't know, but it's got your name on it. He's like, it doesn't, but it does. So then he tried to figure out who, like, find information about that. And both of us like told the AP that reporter shouldn't be reporting anymore on science stuff because she doesn't. I mean, we couldn't even find this. Both of us looked for this for a couple of weeks and passed emails back and forth. Like, did you ever find where that graphic came from, or did she draw that herself? Like, what was the deal? Like, I never found it. So, I mean, it was really cool. I'm like just reading the Sunday Oregonian, and I'm like, oh, cool. There's a nuclear power article, and it's all wrong.